about Thomas Young, who was most famous for his double slit experiments, which prove the wave nature of light. He also did a lot of work on characterising elasticity. The Young's modulus, one of the constants to be found in this experiment, was named in his honour.
So the first thing you want to do is pick up the bar and hang it so that it hangs freely between the jaws of the magnets. Attach the clips to the solder lugs, ensuring the colours match. Make sure the wires are not touching the copper bar. Then switch on both amplifiers, the function generator and the digital oscilloscope. You only need the first channel of this oscilloscope.
The objectives in this experiment were to achieve values for the Young modulus, the shear modulus and the bulk modulus of copper and use these to find its spring constant and its melting point. A way to check your results is to ask the question, why would the melting point of copper be high? Using our chemistry knowledge, we know that copper has metallic bonding. In metallic bonding, the metal cations are uniformly packed together and are surrounded by a sea of delocalized electrons. This means that the thermal energy supplied to the body would have to overcome these strong electrostatic forces of attraction.
In the experiment, you're measuring for the points of resonance which occur at the fundamental frequency, the first overtone, second overtone, and so on.
This is the equation for the bending modes. By plotting a graph of the resonant frequencies against 2n plus 1 all squared, we can calculate the gradient and substitute our known values to calculate y. The second equation is for the torsional modes. We do the same as before by plotting a graph, but this time we use the resonant frequency results from the second bar, and we plot this against n. We substitute our known values again to find s. We find beta using y, which we have already found, and we can then substitute it into this equation to find the speed of sound. We can then sub this speed of sound value into f equals c over 2a, and we can use this frequency to make it equal to 1 over 2 pi times root k over m to find k. With this value of k, we can then substitute it into this equation. A solid will melt when the amplitude is roughly 5% of the interatomic separation, so we must take this into account when substituting in our value of x.
I'm sure you've all heard about Thomas More,